So this brings us to the last class of relations that we are going to talk about, the ordering relations. Now recall equivalence relations, they were reflexive, symmetric, and transitive. And an ordering relation is reflexive, anti-symmetric, and transitive. Okay, so a relation R on set A is called a partial ordering relation, or simply a partial order, if it is reflexive, anti-symmetric, and transitive. Okay, we are going to talk about why we call this partial later on. Okay, and this pair, the relation R along with set A that it is defined on, we call a partially ordered set or poset. Now we denote a partial order usually with this symbol. It's like a cursive smaller than sign. In fact, for instance, in LaTeX, where I prepare these slides, the command for this is PREC. That stands for preceding. Okay, so this one comes before this one, like 3 comes before 5. Okay, so it's not a coincidence that we use this notation similar to less than sign, because less than, along with, let's say, set of integers, is in fact a partial order. And of course, when reflexivity needs to be emphasized, this symbol may be preferred with an equality. Okay, here's an example. Well, less than is not a partial order. Less than or equal is a partial order relation, because, well, you need reflexivity. In the set of integers, less than or equal to defines a poset, or the set of positive integers along with divides defines a poset. Why? Because first of all, it is reflexive. Any number divides itself. Number 2, it's anti-symmetric. If xy and yx, then you have x equals y. You cannot have both ways, like 2 divides 4, but 4 doesn't divide 2. It's anti-symmetric. But if you go both ways, then the number should be equal. 5 divides 5, and 5 divides 5, which means 5 is equal to 5. Okay? And finally, it's transitive. X divides y, and y divides z. This means x also divides z. Therefore, positive integers with the relation divides is a poset. Also, the power set of any set A along with the subset relation is a poset. Why? For any set, S is a subset of itself, right? So you have reflexivity. And if X, well, I need to write like this. If S1 is a subset of S2 and S2 is a subset of S1, this means S1 and S2 are the same set, they are equal, which means you have anti-symmetry in subset relation, okay? Or simply, if two sets are different, if S1 is a subset of S2, then S2 cannot be a subset of S1. Another way of putting it. Finally, you have transitivity. If S1 is a subset of S2 and S2 is a subset of S3, then S1 must be a subset of S3. So the subset relation is, along with a power set, it defines a poset. Now, we say that elements X and Y of a poset are comparable if either X precedes Y or Y precedes X. Either one, okay? If that is not the case, we call them incomparable. This is the reason there is the word partial in partial order, okay? Now, how do we see this? For instance, take integers with less than or equal to. Now, this is not really partial because there are no incomparable elements. Any integers you give me, I can relate them using this relation. But consider this. Let's set S be AB and define the poset, the power set of S with subset. Okay. Now, the empty set, well, of course, the power set of S consists of the empty set, the singletons, B, and the set itself. Right. Now, empty set is a subset of this. It's a subset of this. It's a subset of this. This is a subset of this. This is a subset of this. Of course, all of them are subsets of themselves. But you see, these two, they are not related. They are incomparable. It's not the case that A is a subset of B. And also, it's not the case that B is a subset of A. So in this case, we say that these singletons A and B are incomparable. We cannot compare them, right? Therefore, this is a partial order. It provides an order, but it's not a complete order. What we do not know how to order A and B, okay? So this is the reason we call these partial orders. Now, if all elements can be compared, if they are comparable, like this is a poset, and for all xy, x precedes y or y precedes x. One of these is true for all xy pairs. In this case, which means there is no incomparable elements, then we say this is a total order, okay? Like this here, set of integers along with less than or equal to, because any pair of integers you give me, I can write them using this relation. I can order them. I can compare them, okay? So this is a total order. It's also called a linear order or a chain. But this one is not a total order because set of positive integers, for instance, 2 is related to 4, yes, but 2 is not related to 3. 3 is not related to 2. 2 and 3 are incomparable. So this is a partial order, but it's not a total order. Now this poset is said to be a well-ordered set. Okay, remember this name, well-ordered. If it's a total order and every non-empty subset of A has the least element. For instance, this now is not well-ordered because, for instance, take any subset that goes to negative infinity. Clearly that subset will not have least elements. Least element here corresponds to an element that precedes all other elements. Okay, so here the definition is not satisfied, so this is not well ordered. But if you define it on positive integers, it is now well ordered. Remember the well ordered property we discussed in induction. So there is a very strong relationship here with this definition and well-ordered principle. And this is essentially a definition of a well-ordered set. It's a total order. You have an ordering relation so that you can actually compare two elements. So it should be a total order. That means any two elements you give me, I have to be able to order them or compare them. And if every non-empty subset has a least element, then we say that it's a well-ordered set. And this was the basis of induction, as we have discussed earlier. Okay, so assume that you have a partial order, a poset, and you would like to obtain a total order that doesn't violate any comparisons or any orders in the original poset. Okay, now a total order is said to be compatible with a partial order if this is the case. Okay, if x and y are related through the partial order, this comparison should be preserved in the total order. In this case, we say that they are compatible. Okay, and here's a terminology. An element x is called minimal if there is no element less than x. Okay, there is no element less than x. Doesn't have to be unique, doesn't have to be smaller than all other elements, but it's minimal if there are no elements smaller than it. Now, every finite non-empty poset has a minimal element. You have a finite non-empty poset. It has at least one minimal element. It can have multiple. Okay, for instance, if you define your relation like A less than B, A less than C, let's say your set is A, B, C, A is less than B, A is less than C, or let me add another element, D, and D is also less than B, D is also less than C, okay? But A and D are incomparable. Let's say B also is less than C. Now here you have A less than B less than C, D less than B less than C, but A and D are not comparable. In this case, A and D are minimal elements. So the minimal element doesn't have to be unique. Okay? Now, suppose that you have a poset, you would like to obtain a total order that is compatible with your poset. This is called topological sort, or it's a linearization of a partial order. You have a partial order, you would like to obtain a total order that is compatible. Okay? To do that, to linearize a poset, pick and remove one minimal element at each iteration, and then add it to your total order. For instance, in this one, A and D are minimal elements. For instance, I'm going to pick A, and I remove it from my relation. Okay, what remains is B, C, and D. Among those, the minimal is D, so I'm going to add that and remove it. What remains is BC. Among those, B is the minimal, so put B here, and finally C. Now this here is a total order compatible with my original partial order. Okay, but you see, this is not unique. In the first step, I had selected A because I had two options. I had selected A. I could have selected D, then remove D. What remains is A, B, C, and the minimal among those is A, and then B, and then C. This is also a total order that is compatible with my partial order. So topological sort doesn't give you unique results in every implementation. Okay, so what do we do this? Why do we do this? What is the purpose? Topological sort has applications in project management. For instance, you have some tasks that depend on others to be started. You need the output of one task as the input of the other, so it has to wait for that. That's a precedence. There is an order, a precedence order among the tasks of a project. So in complex projects, you might have a lot of complex relations that may not be simple to observe, but there are softwares that gives you sort of a topological sort. You should do this first and then do this and then do this. Only then you can do this, etc. Or instruction scheduling in a CPU, because you have other operations like input, output, reading, or memory write, memory read, etc. Or some instructions require the output of other instructions, etc. So you have to have sort of a topological sort there to have an order of execution. You have database management applications. Some data, when you need to write it, needs to be written before something else or maybe after something else, or data serialization in digital systems, or software compilation with dependencies. For instance, part of your code depends on the compilation of some other part because it used some functions in there, etc. So in those applications, we use topological sort. And finally, we have the concept of lexicographical order. Sometimes this is also called a dictionary order. Assume that A1 with this relation, A2 with this relation, etc. are all posets. The lexicographical ordering on the Cartesian product A1, A2 through AN is defined is this statement here. Let's say you have an n tuple x1 through xn and another n tuple y1 through yn. When you say this is smaller than this, what you mean is either the first elements x1 is smaller than y1, regardless of the others, or they are equal, but the second elements xy is smaller than y2, or the first two are equal, x1 equal to y1, x2 equal to y1, and the third element, x3 is less than y3. Okay, so it goes on like that. This is what we call lexicographical order, and it has many applications, of course, in again total orders, etc. And it also defines a unique order of structures, so that in fact you can apply induction on structures rather than simple expressions involving numbers. Okay, so this gives you a way to order structures, and this is also related to what we call well-founded induction, which is applicable to structures that are well-founded, meaning that you have a way of ordering each structure and you have a least element. If you have that, you can apply structural induction. This is also called sometimes Noderian induction after Emmy Noether, mathematician and a physician. Very significant contributions also to modern physics as well as mathematics. So lexicographical order is a way to obtain such an order. And it can also be generalized to tuples of different sizes, where you, of course, assume a string, let's say, or a tuple is smaller than another one when all of the first elements that corresponds are equal, but one has smaller size. Okay, so for instance, ABC as a string would be smaller than ABCD, something like this. Okay, so in general, lexicographical order can be generalized to tuples of different sizes, and in a general sense, it provides a way to order structures, which paves the way for a generalized induction approach.